I'd like to present to you Luidhy Santana da Silva. He has a degree in physics from the State University of Ceará in Brazil. He has a master's in astrophysics from the INFI, the National Institute for Space Research in the state of Sao Paulo, and also a PhD in astronomy from the Valongo Observatory in the Federal University of Rio de Janeiro. Where he did also a stay in NASA Goddard Flight Center, Space Flight Center, sorry. I was literally running. He's now, after a couple postdocs, he's now a professor in the Federal University of Rio de Janeiro in doing teaching and research in astronomy and astrophysics. His interests include extragalactic astrophysics, observational cosmology, large photometric surveys, applications of artificial intelligence in astronomy. He's a builder in the DECam Local Volume Exploration Survey, ELF, collaboration, and he has contributed there to the development and scientific exploitation of the survey. So Luidhy, welcome. The microphone is yours.
Thanks, Hannah, for the introduction. So my name is Luidhy Santana, and I'm going to show. Can you hear me well? The volume is okay?
Yes.
Okay. So my name is Luidhy Santana. I'm going to show you is a work that I'm developing for the past. I have been doing this for 7 months or more or less, and the idea of this talk is to show you that AI is not a magic box, but just a tool, and you can use AI for whatever you want to ask to get answers for especially questions in astronomy. So the idea here is to show the classification for the 30 million galaxies in the DELF. It's called the Local Volume Exploration Survey, and this work is a joint effort between Fermilab and CBPF, and now Valongo Observatory. That's the place that I'm professor now. So the first part that you need to make a question is why galaxy morphology and not stellar mass and not star formation rate and not colors, and just why morphology? So morphology, for people that work in extragalactic astronomy, is strongly connected to another properties of the galaxy. So there is clear correlations between morphology and colors, morphology and star formation rate, morphology and stellar mass, morphology, etc. The well-known correlation is the morphology density relation proposed by Dressler in the beginning of the 90s, where basically he found a very clear trend for elliptical galaxies, spiral galaxies, and irregular and the spiral ones regarding the number density of the galaxy. So here in this plot, I'm not sure if you can see the cursor, but here we have in the x-axis, we have the number density, or the number of galaxies for megaparsec square for a given region of the sky. And in the y-axis is the fraction of galaxies. So as you can see here, when the number density increases, the number of elliptical galaxies also increases. And the lenticular also increases. However, when you look to the spiral distribution, the fraction of these galaxies in the sky decrease when you go to high density environments. That means it's basically what we see in galaxy clusters. It's much more common to see elliptical galaxies in the center instead of spirals. So you're going to see spirals in a galaxy cluster in the outskirts of that region. Okay, so this is the first correlation that we know, and that's very well defined. So we know that when the galaxy is elliptical, it's more common to find this type of objects in high density environments. If you just do a simple plot for stellar mass and some colors, in that case U and R, we can see a very different distribution. We can see a bimodality here. We can see a cloud of galaxies in the top and another cloud of galaxies in the bottom. So these regions here are very well known as the red sequence and the blue cloud. In the red sequence, we can see the red dead galaxies, basically the elliptical ones. In the blue cloud, we can see the spiral galaxies, then the regular galaxies. aka the blue ones. And in the middle, we have the green valley. It's a kind of type of transition between these two galaxies types. There is many papers about the galaxies here in the middle, but it's just to show you that when we look to a very simple property of the galaxies, like a color, we can see this tiny difference in that can be connected to the morphology. Oops. So, but all these plots is for the very local universe. We are talking about here redshift like 45. And Lee, in 2023, he investigated the images from the James Webb, and he tried to find, he tried to verify how this galaxy is distributed when you consider different redshift regimes. So for very low redshift, not so low, between redshift 46 and 145, we can see that the elliptical galaxies or the spheroids is still very abundant. Can you, someone is talking or not? Okay. The abundance of elliptical galaxies, you can find a lot of elliptical galaxies in this regime of redshift. However, when you look to the spirals and to the disks and the regulars, the number is not so higher in comparison to the spheroids. And when you go to the cosmic noon, if you remember the Madal plot, where you have the peak of the star formation density is too high, we can see that these numbers start to be a little bit mixed. Like we can see that the fraction of galaxies that can be classified as spheroids, they decrease, is pretty close to the disk ones, but we still can see a tiny difference. And when you go to very, very high redshift, the scenario completely change in comparison to what you see from Dressler's work and also what you see from the cosmic afternoon. Here, the fraction of galaxies literally change in the numbers. So here we can see much more disk galaxies and much less spheroids and irregulars. That means that also the morphology of these galaxies is a kind of trace for the cosmic evolution. Like the small structures is still forming, so they still have a gas. It's not enough time to form ellipticals yet in high redshift. However, when you go to low redshift, the ellipticals start to appear. The galaxy was already evolved, and the whole gas is supposed to be done. That was turned into stars. Okay, so here is the same relation, but for different redshift regimes. Okay, but nowadays it's very easily to classify these galaxies using different methods. But in the very beginning, it was really hard. Hubble started to do that in the 30s. I think it was 1926, maybe. And he was observing the galaxies using the Palomar telescope or Wilson Observatory. I don't remember exactly the name. But the image that he got was something like this. It's basically photographic plates. And he observed that the galaxies have very different features. And these features can be divided in like two groups, the early type galaxies and the late type galaxies. He verified that some galaxies have very bright regions, what we call nowadays the bulge, and there is no structures of gas nearby. And another galaxies have also bulge, a very bright region in the center, but some structures around. So the same here, we have more spiral arms, and here we have we see the spiral arms, and you have the bars close to this bright region that we call the bulge. And Hubble did the first attempt to classify galaxies that is still useful nowadays, but we know that there is more complex. But what Hubble did, Hubble just separated the galaxies in elliptical, lenticular, spirals with no bars, and spirals with bars based on visual classification. So he just looked to the galaxy and he tried to put the galaxy in one of these pockets. Is elliptical, is a spiral, is a lenticular, or is a spiral with bars. Okay, so that works, and is completely fine for our small amount of data. Like if you are classifying 100 galaxies, okay, it's still possible to do that. If you are classifying 1,000 galaxies, we can do that, but for one person, you'll be a little bit tired. And considering the surveys we have right now, like a DELF, DES, DESI, LSST, and many other surveys that's coming in the future and that haven't been done in the past, it's pretty hard to classify these galaxies applying visual classification only. It's almost impossible to finish to classify all that objects. However, the Galaxy Zoo in 2018, 2010, 2011, and I think the last paper was for 2014, they did this very well. But the way that they did this type of classification was using science citizenship to perform this classification. He basically took many images from Sloan and he tried to explain for the normal person, not astronomical, not people into astronomy, and try to okay he gave the picture to these people and he says, oh, if you see spiral arms, this is a spiral galaxy. If you see just a bright center, this should be a elliptical galaxy, and make the classification based on that. And the Galaxy Zoo is well, I think it was the first work of doing this the classification this way using another workforce that's non-astronomical workforce, but he did a very good job. However, they took around 3 or 2 years to classify 1 million galaxies. That's the huge catalog of the galaxies we have right now, and that is used for many other goals, including for machine learning training. And okay, so to classify 1 million galaxies is fine, but if you're thinking about a survey like a DELF and DES, we should have a billion of galaxies, like a 600 million galaxies will be take decades to classify the objects in this way. That's why we use machine learning, deep learning to classify these objects. So we have a much more, it's much more faster than the visual classification and it works so good as the human classification. So there is many examples in the literature where people are using machine learning, deep learning to perform this type of classification. And the next slides, I'm going to convince you that machine learning, deep learning is a good tool to perform this kind of work. But like I told you before, the Hubble classification was very simple. But if you go to just the block of the spiral galaxies, you can see that there is subdivisions. The same thing for the spiral galaxies with bars, and the same thing for the irregular ones. So the visual classification sometimes for a person with no previous knowledge in astronomy will be very hard to classify this type of objects. And applying machine learning techniques, you can avoid this type of error introduced by the human being. Okay, so let me tell you about a DELF. DELF is a survey that we start in 2018. The initial idea of DELF was to observe all the other regions outside the DES footprint. So this black region here is the DES footprint. And we observe basically everything which is outside. In the first moment, we took all the public images made by other observers, by different proposals, and we make the data reduction using the same DES data process pipeline. And we verify that, okay, there is many gaps, and the only place in the South Sky that is well covered is the DES at that moment in 2018, 2017. And the idea for that, and the idea where DELF was born, it is, let's observe everything in a systematic way, observing if the four bands G, R, I, and Z, using the dark energy camera, exactly the same camera, using the DES. And today, this is not the updated plot. Right now, we have a uniform homogeneity coverage for the whole South Sky and for the North Sky up to declination 30 degrees. And we covered around 20,000 square degrees up to 23 magnitudes. And our catalog, this is the 3 billion objects for the DR2 catalog, but the DR3 catalog we are supposed to release by the end of this year have about 4 billion objects. We just observe everything again, visiting the field like 4 times in the past couple of years, that since 2018. Okay, so going back to Delve and just to the morphology project. So the idea is let's do some classification for all galaxies on Delve. Okay, will be easy? No, because we have around limited by magnitude, we have around 600 million galaxies and going magnitude up to 23.45 mags in G band. And at the first moment, we need to decide, we are going to classify everything, even the objects that are very fine, the magnitude is too high, or we are going to put some limits. So for this case, and to make the things less hard, we make a cut in 20, it's not 22 max, it's 21 max in the G band, and we limit all the source for signal to noise higher than 5. In the middle of the presentation, I will explain why. And basically, we built two models. The model one classified the galaxies in two big buckets called disk and spheroids. And the model two, we make a little bit more complex classification. We separate the galaxy between elliptical, lenticular, and spirals and mergers. I put a lenticular in this way because it's very hard to define if the galaxy is a lenticular galaxy or if it is a spiral galaxy edge-on. That's a big problem we have in galaxy classification, especially applying machine learning techniques. There is no clear trend for what is a lenticular exactly in the terms of neural networks. So, and using this model, our goal is to investigate galaxy morphology across different environments and redshifts. And right here, we have 4 examples of spiral galaxies observed on Delve and 2 examples of elliptical galaxies observed on Delve. So visually, it's very easily to classify this as an elliptical and this as a spiral with bars, and this maybe as a spiral with no bars. But imagine to do that for 600 million objects. It'll be very hard to do that and almost impossible. So the selection criteria, as like I told you, is the main catalog is limited to G-band magnitudes below 21.5 mags. And initially we select galaxies just above the galaxy, the Milky Way, be higher than 0. But we did some classification in the middle, include the DES classification. And we're using this type of variable called extended class, which means we are sure that the PSF of the object is not a point source, and so is a galaxy. And the image we use always at least 3 bands to perform the classification. Need to have at least 3 of the 4 bands to perform this. If you have one galaxy with one observation in just only one band, we just remove it from our selection. And we input we need to have the flag 0 to avoid from the observations like things if it is blinding or is not completely separated by the source and so on. We basically the flag 0 from the extractor. And our main catalog right now have 30 million galaxies. And these 30 million galaxies translate into data sets is about 60 terabytes of data, which includes cutouts data and plus data products like catalogs or intermediated images and so on. But you just need to imagine just that for all the 30 million galaxies, you have at least 3 images. So these 30 million stamps translate in 120 million stamps in the scenario that you have the 4 bands observed. But it's about like 100 million stamps in the database that we have. And the logistics to produce these stamps and to get the final products was basically the stamp production was made in Fermilab, the DES machines. Some of the machines are already gone because they are replacing by another machines. And the process to train the models and perform the classification and do the sanity checks was made in SciMind. It's a supercomputer that I'm going to show you the picture in a few minutes in the Brazilian Center for Research in Physics, which it is here in Rio de Janeiro also. Okay, so, but this is not the first work that we are doing about to classify galaxy morphology. As a proof of concept, we did our work in a small survey is in the survey Southern Photometric Local Universe Survey, aka S+, where we classify 160,000 galaxies. So it's a very small number, but was a way to verify if our methodology it's okay before go to the big data. And this was done in 2023 or 24. I don't remember exactly the date. But basically, in this work, we took just very bright objects like a magnitude in the R band below 18, and the region in the sky was like a 10,000 smaller in comparison to that, was just 2,000 square degrees. But what I want to show here is the power of machine learning techniques to identify this source, even when the human being is not able to perform the correct classification. Right here is the image from S+, the small telescope with lower resolution. And in the right side, we have the image from the Legacy survey. Is a data set with much more resolution in comparison to S+. And if you give this image to a person to perform the visual classification here, you cannot say anything about this is an elliptical galaxy or this is a spiral galaxy. You can see just it's a bright pixel in the center of the image. However, applying the neural network while training, we can the neural network predicted this galaxy as a spiral galaxy with 96% of precision. And if you look to the image with high resolution, in fact, this is a spiral galaxy. So even if you have your data with not so good resolution, depends on how you train your model, the classification will be so good as the human eye can perform. So it's a very strong tool to perform this kind of separation between classes and so on. And this is basically the process of the training, how the accuracy evolve and how the laws evolve, which time when epochs means for the people that don't work with machine learning is each epoch we show the training data set, the labeled data to the neural network. In order to the neural network, learning the features in the image and so on. And here is called confusion metrics, where we see how your model is making mistakes or not. So in the y-axis, the actual classification, the real classification, and the x-axis is the predicted classification by the model. So right here, we can see that we make a mistake for late type galaxies just for 6 galaxies. And for early type galaxies, just make a mistake for 24 galaxies. And that's it's very precise. The precision is too high. It's comparable to the human eye. The human eye can classify images with a precision like 99% or 98%, but it takes some hours to classify the same amount of image. Here, we take less than 5 minutes to classify these galaxies. And the results are in agreement with the correlations like the morphology density relation and so on. So these are very strong evidence that using this type of techniques is very important and very strong in the context that we have now many surveys with many images. It would not be possible to invite 1,000 people to classify 1 million galaxies. Okay. So, but what is the problem of convolutional neural networks? The tool is very strong, but they have some weak points. The weak point here is we need a very good training sample. So if you are classifying galaxies as a spiral and ellipticals, we need to be sure that all the galaxies in that training sample are well classified. So this brings us to the problem of the dog and the chicken wing and the chihuahua and the muffin. If you look to the image for 1 second, it will be almost impossible to separate what is a chicken wing or what is a dog, and what is a chihuahua and what is a muffin. But after like 3 seconds, 5 seconds, we start to realize the difference between the dogs and the food. And the same thing happens for the neural networks. When you show your data one time, the neural network is not able to identify the features. But when you show your data for more and more time, the neural network start to adapt to find the features and start to be able to separate the class. And how this thing works, basically, we apply convolutional layers or kernels also in the metrics of the image. And the idea is to reduce the values of different pixels, like we have 5 pixels here, is a matrix of 5 pixels to 5 pixels. In the end of the neural network, we want to reduce this for one single value by applying kernels and convolutional layers. This is another example of how these things work. So basically apply different operations to the pixel, reducing the dimensionality of the image. Like this region here have several numbers of pixels. We reduce this in the end of the day for one single block, for one single value of that region. And in the end, we have a very large array, a flat array with values that will be translated as features for each image. It's like I have a for one class arrays with values equals to 5. And for the other class, I have an array with values equals to 3. And these numbers is a way to perform the separation. We have in the end different arrays, and these arrays have a different numbers. And from these numbers, we can differentiate which class we have. Of course, this will change, depends of your image, depends of the architecture using a neural network. So it's a very large field to perform different experimentations. Okay, so our convolutional neural network was training using 98,000 galaxies in the total sample. For the binary classification was less than 98,000, but for the multi-class classification, which separates galaxies in elliptical, lenticular, spirals, and merger, was the 98,000. And this training sample, the 98,000 galaxies, separates 70% to train, 20% for validation, and 10% for test. And the hardware you use it was the SciMind supercomputer, where I used just one hack to train these models, which compose basically 80 GPUs and NVIDIA IA 5000, which is a very strong hardware in comparison to a domestic computer. It's like if I have a GPU RTX 4050, is one of these GPU is like 3 of these domestic GPUs in terms of memory and in terms of data processing. So here we have 4 examples of images for the 4 class we are looking at. Here we have the elliptical galaxies. Here we have the lenticular ones. Here we have the spirals, and here we have the mergers. So, of course, as I speak this for all my students here, that people think AI is a magic box, but and that can solve all the problems in your life. Not all, but some of them can be solved. But here I do this kind of schema just to show you where AI goes on, because everything starts with the DECam observations that start in 2018. Then we go to the data processing. Then you go to the galaxy selection, not AI yet. Then you go to the stamp production. Then you go to the data transfer, which makes a lot of logistics. And then we extract the image. And then we do the data curation to be sure that we have just galaxies, no stars, no asteroids, no nothing inside the data set. And then you go to the training sample. And the training sample is the part where we start to think about AI. At this moment, I'm just selecting the galaxies that have a very good definition for what it is, like such Galaxy Zoo. I know that galaxies on Galaxy Zoo, I know very well the spiral galaxies, the elliptical ones, and all the morphological types that we can classify within Galaxy Zoo. So this is a kind of training sample we can build. And many people use the Galaxy Zoo, even if it is a small number of galaxies. And after we have the training sample well-defined, we are sure that all the labels are correct, we start the CNN training. And here we perform experimentations for different architectures, because some architectures are good for one type of classification, but for other type of classification is not so good. What I mean by type of classification, I'm doing a binary classification or a multi-class classification. In that case, I'm doing both of them. And it's not every time that the well-established architectures work, especially for galaxies. And sometimes the things doesn't work good and you need to test it. And you lost your time, you lost GPU time to test these things. And after you define your best architecture, you can perform the model evaluation. And the model evaluation, it is basically to identify what is the precision, what is the recall, what is the FU score of your classification. And after we perform the model classification, we can run it in the dataset, which is not classified yet, and you start to perform the sanity checks. Also, I put some sanity checks in the middle just to be sure that our model is classifying okay the training dataset. And then finally, you have the morphological catalog that people can use to perform the science, whatever science you want. Okay, so this is the first attempt that I was doing. This was like 7 months ago, where I was starting the binary classification. The first thing was the first problem, where I find uh, the data with the correct labels was really hard. You can perform the selection in the Galaxy Zoo, but you need to follow all these questions, you need to follow all the percentage of the things in order to define, oh, this is my block of ellipticals, this is my block of spirals. This for just two classes, that's very simple, but I was looking for something more like more mathematical things, not just people opinion. And I found the t-type. Even the t-type was a pretty good problem for me because when you separate the t-type, you can divide for a given t-type value, you have a galaxy type. Like if you consider t-type higher than 1, you are going to select everything that have spiral arms, everything that have some gas component. This can be like a merger, this can be a spiral with bars, this can be a spiral with no bars. And if you selected t-type very slow with very negative values, you are going to get just the elliptical galaxy, the galaxy with a very simple structure. And I started with this test, selecting t-type from galaxies from galaxies classified by Dominguez in 2018. But I found my first problem. I will show to you where the problem goes. And this is basically the distribution of t-type with the galaxies with t-type values calculated by Dominguez in this blue region here in comparison to Delta. So this is the first problem. We don't have a match to all t-type galaxies available in Dominguez with Delta survey. So probably we have less galaxies to train your model in comparison if you have the full data set. That's one problem. So here it is the first diagnostics we have for our training process for the binary classification. Here we see that the curve of accuracy is fine and he grows really fast as expected for any convolutional neural network model. And then he starts to deviate. Okay, that's normal. We have in the training process, we have a precision and accuracy about 95%. And the same thing happens from the loss. The loss basically counts to you when your training data is not well classified during the training test, during the process of training. And here we start to see some problems. Sometimes every time you see a loss curve, which is separated for the validation loss, we call this overfitting. And the overfitting say to us, okay, your training is good, but it's too good for the training process. But when you go to classify the data that was not seen during the training process, your model will not be good. So it's like I'm good to classify X, but when I'm going to classify Y, I cannot classify Y. That's basically what this curve is saying to you, even if the precision is good for the training. And here is the confusion matrix for this binary test classification. We just selected 60,000 galaxies in the test process, which it is galaxies that were not put in the training. So the neural network never saw these galaxies before. So in theory, it's new data. And here in the y-axis, we have the right the actual label. And in the x-axis, we have the predicted class. So we have 3,000 galaxies classified as disk, okay? And we have 3,000 galaxies classified as spheroids. But our model makes mistakes for 40 spheroid galaxies that were classified as disk, and for 150 galaxies that was classified as spheroid, but they are truly disk. So there is a problem in the middle. And here is the point. So even when you are running these machine learning models, you need the sanity checks. The first thing that I think that I tried is let's take a look in the image where the classification was wrong. And these blocks of image in the right side is the Sloan image, the original Sloan image used by Dominguez. And in the left side is the image from Delft. The first difference you can see here is Delft has much more resolution. So originally, this galaxy is classified as a disk. And if you look to the object, okay, maybe it's a disk. I see something bright in the center, and there is this fuzzy region here. Maybe it's the spiral arms. I don't know. But when you go to the image with high resolution, you can see that there is a very bright center and nothing around. So this is a spheroid. And the same things happen for the other galaxies. Here is very clear that the classification, the initial classification from the label data set was wrong, because even the image with low resolution, we can see some kind of structures around. So there is no reason to classify this as a spheroid. So this is basically a problem that even if your data sets should be so good, sometimes human errors are introduced at this side. And especially for this study, I was introducing another error because the image, the original image where the data was labeled, have a lower resolution in comparison to the image that I'm trying to classify the galaxies now. So now this is a big mistake. I should not using this in theory for my classification. I need to find another things. And the way to avoid these things is try to find a galaxy data set well labeled that at least have that at least was observed at the same resolution as your data that you want to classify. And to do this, I using some galaxies from the legacy surveys that have some classification in the Galaxy Zoo, and I performed the classification again just to be sure that the separation is fine. That took like 2 months to perform these things, perform this data curation. And this is the results for the multi-class model using the 98,000 galaxies as a training. In that type of separation, 70% the training, 20% for validation, and 10% for test. Here's the same curves of the growth of accuracy and the decrease of loss. We can see that at some point the training starts to overfitting, and the thing we have to do here is just stop and save the weights of the best epoch in order to classify your unclassified data. And here is the confusion matrix. So this is basically tell us how good your model is and how good your classification is for specific galaxy classes, for specific labels. So as you can see here, the best classifications we find that our model can perform is for elliptical and for spirals. It's very simple because it's the two type of galaxies that the features is very clear. So here we obtain 99% precision and for ellipticals and 99% for spirals. And here is another important message. If you do this type of classification and your model doesn't make any mistake, like a 0.5% mistake, your model probably is wrong, or you had some kind of data leakage during your training process. It's like I trained the model with this number of galaxies, and for some reason, when I go to the test, some galaxies of the training process was in the test sample. This is a kind of data leakage. You need to be very careful about these things when you are training any machine learning model. So these values for these types, for these two specific class, it's fine, especially because is the consider the number of galaxies in the test sample, spirals and ellipticals is the more abundant objects in the in the sample for in the test and the training sample. So the same thing happens for the lenticular. The lenticular, I take this with a big grain of salt because we know that if you have a lenticular galaxy, if someone in the audience have the answer for that, it's really hard to classify. Like if I have a lenticular galaxy or if I have a spiral galaxy edge-on, just look in the image. To us, it's really hard to identify it. And of course, for the neural network, it's also hard to identify it. So the ideal scenario is all the spirals should be edge-on, and if they should be face-on, and if they are edge-on, okay, this is a spiral or this is a lenticular galaxy. That's a big question. And for spiral ones, like I said before, it's very simple. The structure is really hard, really easy to identify the features. But for the mergers is another problem because we don't have too many mergers in the universe tools. We don't have too many mergers in our training sample. And also there is two types of merger. We have the minor mergers and we have the major mergers. Sometimes the image, we have a kind of minor merger that have a very small galaxy in the center of the image and a big one in the outskirts. And it's not every time that the neural network pay attention to these details, because if the galaxy is too small, maybe he will classify only the big one instead of the small one. So it's a kind of data curation that you need to perform after. You need to verify for some classes where your neural networks pay attention inside the image. Usually the galaxies are in the center, but for sometimes the mergers, they are not exactly located in the center. It can perform wrong classification. For instance, 48 galaxies that were merged was classified as a spiral, probably because the spiral galaxy was too big in comparison to the another one, and it's performed this mistake. It's like the human being. And here is the general metrics for the multi-model classification. We have accuracy of 98%, the precision of 97%, the recall 94%, and the FU score 95%. This is common numbers, and that's okay for this type of classification, at least for 4 classes. Okay, so here's the individual values for each class. So again, we do a very good classification for spirals and for ellipticals. But for the mergers, the classification are good, but not so good. So if you are interested to study merger galaxies, we need to be very careful in the classification in the catalog where you are selecting the objects. The another problem, like I told you before, is we test different architectures in order to see what is the best one. So the best architecture is not always that one that gives the best classification. Sometimes you are looking for faster classification instead of to get 100% precision classification. So in this case, we test different traditional architectures with different number of parameters, and the majority of them take around 40 minutes to 70 minutes to run one block of training, like to run 30 epochs. Our architecture, we are still revising this number, reviewing this number, but we take less than 20 minutes. So we perform a better classification to our problem for the problem of multi-class with less time. So considering the computing time that we should be paying, the slow model that will run faster and give to you the best classification is the model that you should use, especially because we use less epochs to train in comparison to the other architectures. But it's very simple. Some of these architectures was not designed to classify the objects we have in our survey. Sometimes they are training for different stamp size. Sometimes the stamp is too big for this classification. Sometimes the stamp is too small. And since we are dealing with a large survey, we need to perform the stamp production with a standard pattern, a standard size. And sometimes the standard size is not compatible with the weights of the architecture was training originally. So that's why we choose our new model. These are very preliminary results where we start to using our classification made by our model, take just elliptical and spiral class and see how the things change with the environment. Here is the environment, the x-axis is the environmental density using the nearest neighbor method. And here we can see a kind of, it's not a kind of, here you can see the morphology density relation itself. So here we see that the spiral galaxies decay the number when you go to high density environments, and the elliptical galaxies increase the fraction when you go to high density environments. So basically here we are looking at center of the galaxy clusters, and here we are looking at to the outskirts of the galaxy clusters or spiral galaxies in the field. So the next step is to verify another correlation. So basically this was a result from 2 weeks ago. I don't remember exactly how many galaxies we have here, but it's something like 10 million galaxies in this plot. We are not analyzing yet the other 20 million. Okay, so this is the summary of my presentation. So galaxy morphology plays an important role to understand galaxy formation evolution, especially because the morphology is connected with different galaxy properties. The amount of data we have right now turns almost impossible to classify galaxies using visual inspection. But you can do something similar to Galaxy Zoo also, but it take much more time to classify like 20 billion galaxies and 30 million galaxies. And the model precision that we obtain with Delph in these models is pretty similar to the human eye. If you obtain something that's not very similar, it's a red flag. So your model have a problem or your training sample have a problem. And so far we classified 20 million galaxies already done. Is the galaxies inside that limits of the sky and that limit of magnitude, but we are planning to apply the whole classification to the whole galaxies in the Delph footprint, which is 700 million galaxies, but we got the problem that our model was training with galaxies that have some limit of magnitude. If you go deeper than that, we can start to see very strong mistakes in the classification for a galaxy that have a low surface brightness that were not took in consideration during the training process. So the steps we are running right now is we are preparing the catalog to release the morphological classification for both catalogs, for the binary classification, for the complex classification. And now we are also exploring how our morphological classification connects with the environment of the galaxy. So take into account clusters, small groups, and so on. So that's it for all, and hopefully next year I will have the final results for everything. Thanks.
Thank you very much, Luigi. Do we have any questions in the auditorium? Let's see some hands. Okay, Jacopo first.
Hi, thanks for the talk. I maybe was a little bit confused. So you're talking about binary classification, so early and late types, and then dividing in like elliptical, zero, and spirals, and then the T-type classifications. But so your performance, the performance that actually you're showing here in this slide, what do they refer to? Which like morphological classification subdivision? Which one of the three?
This one? In the final. Wait, I didn't catch your question. So you're asking which classification are you putting in the catalog, right?
Well, or to which of the three different classifications, so binary and then
and then multi-class.
Yeah, and the T-type. So which one your performance referred to?
The performances here refer to the binary classification using the T-type. This slide, okay? I just use the T-type for binary classification.
Okay. So you classify, you give a t-type, but then you just smooth your classification, basically.
Yes,
Okay.
yes. Because when you use the t-type higher than 1, you took everything that looks like a disk, like will be spiral galaxies, mergers, everything will be in that pocket. Because I'm using a large value of t-type. Everything that's higher than 1, I will consider as a disk.
Okay.
And that's the only difference. Here, for the multi-class classification, we used a Galaxy Zoo that was done using the DECam images that were in the same resolution of the image of Delft. And in that way, I avoid the mistakes that I showed to you here. Because the difference here in the classification is not the t-type. The t-type is fine, but when I go to the image with high resolution, the classification changes. He's not a disk. He's a spheroid per se. And that's a kind of, it's like that was a way to avoid introducing these errors to my final model. Because even if the t-type, the image itself have an influence in the classification, because we need the best scenario is we have an image with high resolution that you can see all details of the galaxy. That's not the case. So this is a kind of error introduced in the training sample. And to avoid it, the only way is try to get an image in the same resolution.
Okay.
Raul, you had a question?
Yes, thank you very much for the talk. I'm wondering about how easily you can apply this method of classification to other radio wavelengths for identify galaxies. So, for example, identify new radio galaxies in radio wavelength maps, for example. Is it easy to use it, or you have to do extra work?
I'm not into radio galaxies, so if you have different bands, it's like if radio galaxies have a different energy levels, like different bands for my photometry, we can apply it, but pay attention to apply neural networks, you need a very good training sample. If you know a sample of radio galaxies well identified and well classified, you can apply neural networks anyway. But you need to have the training sample. And if it's not labeled, if you don't have a good label for this training sample, it's a problem. The problem is not the method itself, but how you select your galaxies to train. I'm not sure if I answer your question, but you can apply CNN for whatever you want, since if you have a good training sample.
Okay, thank you.
Any other questions? Oh, yeah.
Thank you for the talk. Have you tried to train your models using numerical simulations of cosmological numerical simulations?
Can you say again?
Yeah, have you tried to train your model with the numerical simulations like Illustris or something like that?
Using the images from Illustris, TNG, and so on. Yeah, this is in my plan for the next semester. However, I didn't do that at first point because the main goal of the survey was to classify the galaxies in the Delft. And if I got the images in cosmological simulation, maybe I need to perform some kind of degradation to make the image worse as in real life to perform the training. But I saw some works that people are using image for cosmological simulation to training, but usually they are looking for very specific objects like dwarf galaxies and these things, not like simple like spiral ellipticals and so on.
And does it help? Or
what?
Does it help?
It affects because you take the image with the best resolution and then you need to downgrade that thing. The only advantage is you don't have a lot of work to select the galaxies because the images inside the cosmological simulation are well defined. So we just need, okay, everything that is a spiral that have a halo mass of this size is spiral, and I took everything from that. In the real life is much more complicated because you are dealing with you are dealing with signal to noise variation. The sky conditions for the survey is not every time is homogeneous. Sometimes one epoch is very good, the other epoch is not so good, and they take it out of the survey. But the big problem here, and that cosmological simulation can solve, is the resolution. You can take the image from the cosmological simulation and manipulate for different resolutions, whatever you want. And this, of course, is a plus to perform your training. But the big question is, if I do that, I will make my data set representative of the real life. That's the point. You can make a very good training, but the model sometimes cannot generalize in common data sets, in the ordinary data we found. But many people do this kind of synthetic data to train.
You have time for one more question? Yeah.
Have you identified any bias with your selection or your classification, for instance, with the inclination or axis ratio of the objects, or the color if the classification is made with composite images?
I didn't found this yet. This is in the part of the sanity check, because in the selection process, I'm just taking into account the votes from the Galaxy Zoo DECaLS, the people did it. But this is something that you need to take into account also especially for taking some data from like a large sky surveys, you have some limitations, and the only bias that I found was that about the resolution. So everything was changing, and I start to find many wrong classifications that's not supposed to be there. And when I look at the image, the only problem was the resolution. But this is something we find in the middle. We just tell you the good story. We avoid the mistakes in the middle.
One more question? Anyone?
Morgan.
Yeah, go ahead.
So you mentioned photometric Z, like to construct, for example, the morphology density relation. Are you going to do that with neural network as well? Or, for example, you could also use your method for stellar mass calculations. I mean, because I guess there are many galaxies that you can use as a training set, right?
Yes. You can use this also, but I did this just for sanity check. I was just to be sure that my classification can recover with the common relations, but you can do with other things like stellar mass and so on.
Did you have a question? Yeah. Okay. Let's thank Luidhy again.
Thank you.
Thanks a lot, Luidhy. I'll send you an email later.
Okay. Thanks, Hannah. Good to see you.
Renee. Oh, Renee. Luidhy saying good to see you. Okay. Renee is too busy talking.
Okay.
He's on the way. He's on the way.
Es que a mí no me llegan correos. No sé, y no me llegan. Entonces, te digo porque me encontré el cigarrito. ¡Hey, Luigi! Oi!
So the next step is to invite you to here to give a talk to us.
I don't know if I should do that. I'm not doing any science recently. I'm just doing outreach.
Oh, but we have an outreach part here made by Paula Freni. Maybe it's a good.
Yeah. Well, if I can talk about, I can like I've done here. I can give a talk about outreach, not an outreach talk, but a talk about outreach.
Okay, so that's be good. Okay.
Yeah. Tudo bem?
Tudo. Agora é fazer outras coisas, mas enfim. Espero que o pessoal tenha conseguido entender que é a primeira vez que eu dou talk online, cara. Eu acho muito estranho.
É mesmo. Há quanto tempo está você no Rio como professor?
Acho que vai fazer 3 meses agora.
Sim.
Esse tempo,
Apenas. Uhum.
esse tempo todo eu estava em São Paulo. Aí ano
Ah,
passado eu passei um tempo no Fermilab.
sim.
Aí eu voltei basicamente para fazer a prova.
Mas você estiveu também no CBPF?
Sim, sim. Aí
Sim.
eu tava lá. Aí em 2024 eu fui para o Fermilab. Eu fiquei uns 7 meses lá.
Tá.
Mas enfim,
Muito bom.
agora eu vou parar no lugar certo agora pelos próximos 20 anos.
Sim.
Tá
Bom,
bom.
fala oi para o Tiago, a Karen, todo mundo por lá. Marco está lá também?
Sim, o Marco é professor daqui. Ele entrou
Tá.
acho que faz uns 3 anos já.
Ah, que legal.
Pronto.
Bom,
Be-
fala oi para todo mundo lá.
Beleza, beleza. Pode te ver, René. Tchau, tchau.
Tchau.
Bye.
Tchau, tchau.